All right, welcome everyone. Today we're going to start our next big discussion, our next big chapter, looking at double integrals. Okay, so let me start to share the doc in and we'll get going. All right, so as we get started, we're going to be looking at these double integrals over rectangular regions. So we're going to start off with our domain space, our region over which we're integrating. We're going to look at the region being a rectangle. Okay, and then in the next section will be a nice tie-in. We'll start to see more general blob type regions, right? Blob, where it's not a nice simple rectangle to manage. But again, with all that of this discussion, as we've been talking about, I'm always going to tie it back into our first semester calculus, right? So in Calc 1, right, Math 28 here, MPC, remember that our integral corresponded to that area under a curve, right? Or the amount, the net total area trapped underneath in between the x-axis and our function. Our function is y, a function of x, right? And so when we looked at that, having our function f of x, we looked at some segment, some interval over the x-axis, or some interval of the x-axis, and then that integral would exactly be, right, that amount of area. And again, we could dip below the x-axis, have a negative result, right? But we would say that that area is equal to this integral from a to b of our function f of x dx, right, that integrating factor. And even there, visually, we even went a step further about kind of how would we approximate that area to begin with? How will we get that quantity? Right? Remember that we used small rectangles to approximate that area, that integral. And that's where that limit definition came in as well, trying to let the number of subintervals, the number of rectangles that we're using to fill that space go to infinity, right? Those little slivers, and adding up all of those, taking that summation, that became the integral symbol, right, along that interval from A to B. All right, so with that said, now in our Calc 3 course, Math 20C now our double integral that's going to correspond to the amount of volume under a surface. Okay, so visualizing here, and again, drawing this is always a task in itself. But suppose we have now, right, this surface this function of x and y, and suppose we want to integrate over, we'll start off with some rectangular region. Okay, so in that aspect, x is going to be between some quantities a and b, y plus x, sorry. And then y, I got my arrows mixed up here, sorry folks. Y is going to be between some quantity C and D. There we go. Better. A little bit wonky there, right? We're letting x go between these values, y between those values, okay? And so, just as we kind of looked at these little rectangles, now what we kind of imagine is that we're going to have these little columns, I call them, of volume. Right? So now we're going to be imagining taking all these little rectangular prisms, right? All these little columns over that region that we're integrating over and adding up those quantities. So in this case, that total volume, once I start to get below this entire space, okay, filling up that entire region with those little columns, is going to be this double integral of our function, okay? But now we're going to have what we call this quantity dA, and we're going to integrate over this region R. So that R, or in some cases, I think we'll use a D, this domain space, okay? This is the region over which we're integrating, dA. This is going to corresponding to like our area of the base of our column. Right, so we're going to add up all those columns to get that volume. Add up the volumes of each column. We're going to get that total space, right? And so what we're going to kind of start to see is that volume integrating over that region for our function. So we're going to start to apply either a dx dy, dy dx. The order we'll see can change, but just keep track. If we're doing x first, is going from A to B. Y secondly is going from C to D. Right, that outer variable, checking its limits. Inner variable, what we're integrating first, what its limits of integration will be. Because think about that little column in this rectangular prism. The base is going to be that rectangle, square, a little dx width, a little dy length. To get the area of the base, dx times dy, length times width, width times length, whatever you want to call it. That's what the little space is called. Okay, so let me kind of make that image a little bigger. Okay, so in that aspect though, right, each column of volume looks like the following, where we have that rectangular base, where we have a little width dx, length dy, okay, and then that height given like so, okay. So let me do something quick. Sorry for that little bit of a poor drawing here, but we can see, right, that portion of that base here, dA, right, that's just our area of this base. And then that height, that's going to be the z value, which comes from your function, right? So every little component, right? Each component, each little piece of volume that we add, the little change in volume, that little piece of volume is going to be, right, our height times that dA times the area of the base or when we start to extend it out, thinking about that, we can either go dx, dy, or similar, dy, dx. We don't have to put the multiplication dots, but for practice of seeing how that's a volume, right? We're multiplying height times length times width, right? And then we're going to add up all of those to get that total volume. Okay, so that kind of aspect, kind of having that visualization, hopefully, can support when we start to do calculations, when we start to see those problems, help us organize and put these pieces together. Okay, and so just like we had done with our integrals in Math 28, our first semester calculus, thinking, okay, I'm starting when x equals 0, going to x equals 5, or I'm integrating over 1 to 4, whatever it is. We saw that same idea in terms of those limits of integration for x, for y, and we just have to keep track over that region that we're integrating, okay, what those limits look like. And as we go through, we'll start to see that the order in which we integrate doesn't necessarily make a difference as long as we keep track of what those limits need to be for those differing variables. And that's a little bit more interesting discussion when we start integrating over general regions, as we'll talk about in the next lecture, in the next discussion. Okay, so let's look at a problem here, or a discussion first, and we'll get into an actual calculation problem. So when we evaluate a double integral, pardon me, right? So we're looking at this integral, integrating over some region R. So it's not just a single variable that we have to deal with. There's going to be more than one variable, typically x and y. And again, I'll put a dA. It can either be a case when we have, I'm going to leave it R, that integrating factor dA becomes dx dy, or integrating that region R, f of xy, dy, dx. So depending on which integrating factor is listed first, we must make sure the limits correspond, right? The limits of integration. Let's put that in there. To the correct variable, right? So if we're integrating with respect to y first, we want to make sure on that first integral symbol, we have the appropriate limits of integration to go along with that y. And likewise for x, okay? And so then Next statement, as we integrate, right, as we go through that first integration, keep in mind that integrating factor, that integrating variable, just like partial derivatives, when we're doing a partial derivative, taking a partial respect to x, a partial respect to y, that other variable involved is considered a constant. Okay, push that up. So as we go through it, if I'm integrating with respect to y, I'm going to consider any x I see as just a constant. Because kind of what we're thinking about, what we're going to start to visualize is that when we start to go through, I'm going to let that y, for instance, go between those values between c and d. But I'm going to imagine, okay, I'm going to let x equal a first and handle all of those little rectangles in that direction. Then I'm going to let x be another value, hold it constant, and take all the little y's, taking a little step along this path, building up all those columns. So that's what we're kind of keep in mind. Just like with our partial derivatives, we're imagining we're holding x constant, and I'm going to see how y varies in that line, in that contour. We're doing the same thing now with these volumes, these integrals. We're going to consider, okay, if I'm going to follow one set value for x, how is my y values taking steps in that direction from c to d, getting up all those components, and vice versa. I can hold y constant and let x vary between a and b. We have to keep track of which variable we're dealing with in that time. Okay, so watch those components to keep track. Okay, and so one more time here with that volume being that integral, that double integral of our function, right? That's giving us our height, f of x, y, dA. Now, keeping track, if we're going to do this integral in this order, that if I do dx first, that x is going from a to b. Okay, you can say, okay, there's my inner integral, if you will. We'll do that work. X is the variable, y is going to be considered constant, and then we'll get that answer. dy is going from c to d. Then once you get that result, you'll most likely have some expression left with y, and now you'll fill in that expression and compute this integral. So it's going to be like two of those first semester calculus integrals. We're just kind of layering them together, right? Or likewise, if we do it the opposite direction, if I do my dx as my outer, it's going from a to b, dy from my inner is going from c to d, and we still have our function f of x, y. So now for the first integral we do is going to be with respect to y, x is a constant. Carrying that out, get that answer, and then do the result, that integral with respect to x. Okay, again, still a little bit abstract since I've just written this out. Let's see an example. Okay, so for this example, let's check out this one. Integrating over the region R of our function 2x plus 1 dA, and this region R that we're dealing with, again, in this section, in this lecture, we're only talking about rectangular regions. So we're integrating over the set of ordered pairs, this rectangle, where x goes from 0 to 2, and y goes from 0 to 4. Okay. So in that aspect, again, I'm not going to worry necessarily about graphing my surface, though we could. I'm more interested in this aspect. Okay, x is going to go between 0 and 2. Y is going to go between 0 to 4. So our region over which we're integrating that's our R, that rectangular region. And so again, without drawing in the actual surface, I'm going to imagine we have, there's my little dA, that we're going to build this column of volume 4. And that's what I call it. I don't think the textbook calls it this. But that's what we can imagine building up and adding all these together. Okay? All right, so now when that's said, okay, so this is my function. There's no dependence on y, but that's my height, okay? And when we have a rectangular region where the x and y are just constants, it's not going to make a difference which order we use. And we can show that calculation that I can integrate respect to y last from 0 to 4, x first from 0 to 2, and then our function 2x plus 1. So I can take this integral from 0 to 4 dy from 0 to 2 dx of our function 2x plus 1. So when we compute, exactly, we're going to do this kind of interior integral first. So when I do that, just thinking about, okay, if I was to integrate from 0 to 2x plus 1 dx, right, our fundamental theorem of calculus, back to 20a, that power rule, x squared plus x. Since I have a definite integral, there's no constant integration here, we're going to evaluate from 0 to 2. Or I guess I could say 2 squared plus 2 minus 0 squared plus 0, 4 plus 2, 6. Right, so that whole integral is a constant. It is equal to 6. So this becomes then this integral from 0 to 4 of 6 dy. Integrate here, that's just a constant. So that's 6 stays. Now we're integrating respect to y. Y goes there, and we're integrating, and we're evaluating from 4 to 0. And so when evaluating, 6 times 4 minus 6 times 0 equaling 24. So that integral of that function, 2x plus 1, a double integral of that function, a surface 2x plus 1 over that region R, so that area over which we're integrating is 24, right? So the volume would be 24 cubic units, right? Inches cubed, centimeters, whatever we're using to measure. So we get some solid, one of our definite intervals, some solid numerical result. So let's just compare our result if we integrate with respect to y first? We should get the same answer, right? Still the same surface, the same region, the same R rectangle, right? But now let's say we're going to integrate with respect to y first. So x is outside from 0 to 2. Y is inside from 0 to 4. And the same function, 2x plus 1. So remember, y is the variable, x is a constant. So in this case, whether you want to go term by term, let's go here, or just see that that entire 2x plus 1 is a constant, we can say that we get 2x y plus 1 y evaluated from 4 to 0. Right? X is just a constant, like a pi. It's going to stick around. So that's going to be 2x times 4 plus 1 times 4 minus 2x times 0 plus 1 times 0. Right? There's my y values. 2x times 4 is 8x plus 4, 0, 0, right? Move that out of the way. So there's my expression. Notice we have that result still has a variable involved. It's not a constant like last time, but that's okay. Because now we're integrating with respect to x last, and that 8x plus 4, having that x variable, is going to be okay. So then when we start to compute, right, our power rule again, 8x stays. Oh, sorry, not stays. Sorry, we're integrating with x. 8x becomes, right, 8x squared over 2, or 4x, plus 4x squared, sorry, going too fast in my head. Doing that power rule, 4x squared, there we go, plus 4x. You got 2 and 0. Computing here. Plugging in, 2's, 0's. And what are we going to get? 4 times 4 plus 8 minus 0. 16 plus 8. And look at that. 24, the same exact result. Right? So regardless of which variable we choose to integrate with respect to first or second, we'll get the same final answer no matter what. Okay? And it's just up to you which might be easier, because when we start to get to our more general regions in the next section, those limits of integration become a little bit more interesting. We have to be very careful on how we organize. Okay? But there's a good introduction. The big component here in our realm of thinking is how this double integral, I'm starting to visualize as this kind of compilation, this build up all these little columns of volume to fill that space underneath our surface. Okay? All right, if questions there, let me know. Otherwise, we'll be back with a more interesting double integral in the next lecture.